Hello, this is chapter 17, question number 74. Time in a restaurant. The owner of a pizza restaurant in France knows that the time customers spend in the restaurant on a Saturday evening has a mean of 90 minutes and a standard deviation 15 minutes. He has read that pleasant odors can influence customers, so he spreads a lavender odor throughout the restaurant. Here are the times and minutes for customers on the next Saturday evening. And this is based on real research, and this is a real set of data from this experiment. And so we can see here we have looks like about 30. It looks like around 30 customers, and here's the times they spent in the restaurant. The fastest customers were 76 minutes. The slowest customers 124 minutes. But after a quick glance, it does look like, on average, it is more than 90 minutes. So it looks like I would have to guess that this lavender odor really is influencing behavior. On average, it is causing people to stay longer here in the restaurant. Now, uh, we'll get to part A and B in a moment here, but part A is um, is basically asking the question: Is it legitimate to use a normal curve for the sampling distribution? That's what part A is all about. Uh, so let's just review um, a couple of things here real quick. Back from chapter 11, the central limit theorem, um, it says, central limit theorem, it says a few things. The first thing it says is if the population is normal, then automatically, then the sampling distribution is normal. All right. Well, that makes sense. Um, and you remember in most homework problems up to this point, the question would always say blah 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 blah, comma such and such is normal, comma what is the confidence interval, or do a hypothesis test or something like that. And so you just assumed a normal population, so then the sampling distribution is normal. Okay, on this problem though, chapter 17, question 74, there's no indication here that we have a normal distribution. And so we can't automatically assume the sampling distribution is going to be normal. So let's go back to revisit the rules here. Oop, wrong way. Okay, so that was part one of the central limit theorem. Part two of the central limit theorem says that if the population is not normal, then as n gets larger, the sampling distribution gets closer to a normal distribution. So the sampling distribution gets close, or it gets closer to normal. Okay. So how large is large enough? How close is close enough? Well, in general, if your population is skewed, then you need to have a larger n. N must be relatively larger than it otherwise would need to be. Usually more than 40. I'd have to say, if I had to pick a number, I'd say 40. Okay. Now, in this case, in this problem, our sample size is not 40. It's around 30, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 3 rows, 10, n is 30. So if we had a skewed population, we'd be in trouble. However, back to our rules here. But if the population is not skewed, so it may not be normal, but at least if it's not skewed, if it's somewhat symmetric, if it's unimodal symmetric, now maybe that means it's normal, maybe it's not, because not all unimodal symmetric distributions are automatically normal. But if it is unimodal and symmetric, then n doesn't have to be quite so big. And you can still have a normal distribution. N doesn't have to be as big. So I would say if n is at least, 10 or so, it would be big enough. All right, so that's what question A is all about. So now, after revisiting these rules a little bit, let's go back to the question here. So question 8 says, make a stem plot of the times. The distribution is roughly symmetric, single peaked, so the distribution of x bar should be close to normal. All right, so let's go. I made a stem plot just to save a little bit of time here. Oop. Here it is. Okay, so here's a stem plot of the times. And you can see that in general, the sample, now I still don't know for sure what the population looks like, and I'm never going to know the population distribution, but I can say that the sample is unimodal and symmetric. All right. Now, if your sample is unimodal and symmetric, then probably that means your population is unimodal symmetric. Now, it's possible there could be someone in the population that would stay in the restaurant for 1,000 minutes and it didn't show up in the sample, and it skews the population. But usually, if there is a skew in the population that would have shown up in a sample, at least one large number would, or small number would have shown up. But I don't see any skews here in the sample, so probably the population is unimodal and symmetric. Now, there's no guarantees here, but at least it's reasonable to assume that. All right, and if your population is unimodal and symmetric, then that means, back to our rules we talked about earlier here, if the population is unimodal symmetric, then n doesn't have to be quite so big. All right, so 30 is big enough. So I can say then the sampling distribution for this situation here, n being 30, will be close to normal. And close enough that we can use the z-scores and the normal distribution to get our answers. Okay, so that's the whole point of part A to question 74. All right, now let's do part B to this problem.